gamma is the object when it's written as component wise, like. So now we can actually conclude that our small gamma 1, 2, by the way, is this result correct? Can you check it again, please?
I think there should be a division of 2 here.
I think so, yes. Instead of like, I
Yeah,
think
it
the
should
result is
be.
correct actually.
Big gamma 1 2 is equal to half times gamma 1 2 minus gamma 2 1.
Yeah,
Yes, that it should be, yes. What? Half?
Just multiply half
just
and put
multiply
it
half.
inside
Yeah,
the bracket. Half
Mm,
times gamma 1 2 minus gamma 2 1. That's right.
that doesn't seem right again. There should be more actually. Like it should be opposite. Small gamma 2, 1 should be the double of the other thing. Or let's do the algebra. So gamma 1 2 minus gamma 2 1 equals to gamma 1 2, and then gamma 2 1 minus gamma 1 2 equals to small gamma 2 1. So if I add no, if I can subtract those two terms, right? If I subtract this term, then this thing becomes minus, this thing becomes plus, this thing becomes minus, right?
yeah,
This algebra is wrong. Sorry. This algebra is wrong.
sorry.
Okay. So what do you get? These two things are same. So twice gamma 1 2, right? Then minus twice gamma 2 1 equals to gamma 1 2 minus gamma 2 1.
Yeah,
Okay. So using again the symmetry property, we can actually have gamma what 1 2 twice gamma 1 2, like that. So basically the only independent relation here is this gamma 1 2 minus gamma 2 1. It has to be equal to gamma 1 2, like that. Now as the whole thing is in like antisymmetric, so we can demand like like as you can see, like we have like one totally indeterminate component, right? Like gamma 2 1, you can at max find one of those, not both, right? Because these two are like dependent equations, these are not independent.
yeah,
So we can demand like the same antisymmetry, because it's a complete antisymmetric object. The same antisymmetry relation happens for big gamma as well. So if we demand like big gamma 2 1 to be like negative big gamma 1 2, then what do we get? We get twice gamma 1 2 equals to gamma 1 2, like that. So that gives us big gamma 1 2 equals to half of gamma small gamma 1 2, like that. This is the relation actually we have been seeking. So this thing this thing holds for any other components. So whenever you want to write so let's summarize. So you have seen this half factor over there. So whenever you want to write a 0 to tensor, like a 2 form, you have a 2 form, but written as in terms of like tensor basis, 0 to tensor basis. So your gamma should be like this: gamma mu nu say omega mu times omega nu, like that. But if you want to write the same thing in terms of wedge product, like the basis of two form itself, then you have to be a little bit clever by putting this half in front of it. So half gamma mu nu omega mu wedge omega nu. That's the same thing here. This gamma and this gamma are same. So these are the component of like 0 to 0 to tensors. So and this whole thing like half gamma mu nu, this is the we usually call it component of two form. Is that clear to everyone? This is due to the antisymmetry property. So basically we expand this thing if you do the same algebra for a three form, say. So for a three form, what you will get if you do this, that your gamma, let's call it beta. Its beta is a three form. Then if you want to write it as a 0,3 tensor in terms of 0,3 tensor component basis, then it will be like beta mu nu lambda, like that, because it should have three indices. Then omega mu times omega nu times omega lambda, like that. It's a 0,3 tensor. Then if you want to write in terms of like you want something in front, but you want like this: omega mu wedge omega nu wedge omega lambda. Then what happens? What should you write here? Any guess? You have just seen one example, so it's hard to tell. But yeah, just have some weird. Why did you guess that?
2 factorial. I
Yes,
thought
it's
it can be, yeah, 2 factorial.
basically 2 factorial. Yes.
Yeah.
So in general, a P form or whichever object can be written as like this. Say some alpha, which we can write in terms of wedge product. A P form can be written like this: 1 over P factorial. Alpha should have now P indices. So alpha, say mu1 is the first index, alpha mu2 is the second index. So remember now mu1, mu2 are wholly like in whole, those are indices. So mu1 runs from like 0 to n for n dimension, like that. And so on for mu2 and so it will have P indices, so up to mu P, then omega mu1 wedge omega mu2 wedge up to omega mu P, like that. This is when you write in terms of wedge product. But when you write in terms of direct product, that means the usual 0P tensor, what you should expect? Any guess? Ms. Bajaj?
Yes.
Is just this part. Like that. That's it. So a P form is an object that can be written like this, basically. So it's a linear combination of wedge products of P number of one forms, right?
Yeah.
Okay. We'll see application in a moment. Just hang on and let's see the product rule first. Then we'll see application, actually, electromagnetic case. Okay. Now. We have a general P form. So now we want the general definition of wedge product as well. So wedge product, we defined slopily so far in terms of direct product, right? We have already defined, but a general definition that can be applied directly. is like defined by three properties. First of all, linearity. That means if you have three one forms, so one is alpha, another is beta, and their combination is written like some a is a number times alpha plus b is a number times beta, and you take wedge product with a third third one form. It need not to be a one form actually, so it's any form like p form, q form, or r form, doesn't matter. So for any p form, any kind of p form, alpha, beta, and gamma, this linearity property should hold. That is a times alpha wedge gamma plus b times beta wedge gamma. So that's a defining property. Then another defining property is associativity. That is when you have when you do this thing, then do this thing, that should be equal to doing this thing first. Actually, I wanted to write alpha. Doing this thing first. Sorry, I already did that. Doing this thing first, beta wedge gamma, then taking alpha, which is basically written as like this. So the order should not matter, which order you performed. Which two things you took wedge product first and then took with which, it doesn't matter. It's like associative property of addition, like you can add two things first and then with the third one, the order doesn't matter. Like that. But you remember cross product wasn't like this, right? When you did cross product in elementary vector algebra, it wasn't like this. Okay, and the third defining property is if alpha is a p form, specifically we are saying now, and beta is a q form, then alpha wedge beta should be equal to -1 whole to the power p times q beta wedge alpha. These three are the fundamental defining properties of wedge product. You can apply this thing to any arbitrary p forms. So let's apply for 2-1 form, then we'll understand. So if alpha and beta are one form, then alpha wedge beta should be equal to -1 whole to the power 1 times 1 beta wedge alpha, right? Which is basically negative beta wedge alpha. And that matches with our original definition, right? Just remember these three things. These are the fundamental defining properties. Now we are defining it formally. Okay, with this three definition, can you prove that alpha wedge alpha is 0? Can you prove that for any arbitrary p form? For any arbitrary p form, alpha wedge alpha equals to 0. Can you prove that?
Yeah, we can use the third one, I think.
Yes, we can use this one. So yes, tell me what to do.
Alpha
Alpha,
with alpha
alpha, yes,
is
equal to
equal to
alpha is a so -1
p squared.
p squared. Mhm. Then
So it will
alpha,
be +1.
no, it's not going to be +1.
Mm,
For alpha being odd,
yeah, sorry.
for alpha, when alpha is like p is odd, then obviously it's equals to minus alpha wedge alpha. Hmm?
Yeah, in that case,
In that case, it's 0.
0.
But what if
Yeah.
p is even? It's a two form, say.
Uh, I guess we can't conclude anything from this expression because it will
Yes.
be both sides 0.
Yes, we cannot conclude. So which one can we use to show anything? Hmm? So basically, when you are dealing with even forms, you cannot actually cancel this kind of terms. You have to be careful. So these are not generally 0. It's 0 for odd ones. Hmm?
Okay.
Okay.
But didn't we? Oh no, they were one forms. Those bases.
No. Whenever you have two form, you have to take the wedge product appropriately. Otherwise, it won't work. But yes, if it is in 2-dimension, then it's 0. But that's 0 for another reason.
Why?
We'll see. In n dimension, if you have a p form, the p form will automatically become 0, some alpha equals to 0, if p is greater than n. So when you take wedge product of these two things, so 2 plus 2 is totally 4 form, but in 3-dimension, that satisfies this condition. There is a reason why it happens. We'll see. We'll see. Okay. We need to see one more thing actually, but that's gonna be really abstract at this point. So let's wait a little bit. We wanted to see piercing, but let's wait. Okay, let's do a little bit more algebra. So say your alpha is a 1 form and beta is a 1 form. So we can write our alpha to be like, say alpha I omega I, right? Like that. And our beta to be like beta j omega j, like that.
Yeah.
So what should be the components, like components of alpha wedge beta? So obviously that gives us like alpha I beta j omega I wedge omega j, right?
Yeah.
Okay, so but we want to write in terms of our direct product, that's our components, right? We want to find the components appropriately. So here whatever you get, it's not basically the components is when you write everything in terms of direct product, right? So component of this tensor. So okay, these are components as well, but okay, we usually do not write like that. Okay, so basically what I want to do is like this, omega I times omega j, where I and j as are summed over, minus omega j times omega I, right? We can do that.
Yeah.
Now, we have alpha I beta j, omega I times omega j, that's fine. But then I have alpha I beta j omega j times omega I, right?
Hmm.
Now, our indices here, I and j, both are dummy indices, so we can replace with anything, right? I want to replace this I to be j, and this j to be I. Can you tell me why I did that? To match with this part. Then I can actually factor out, right? Factor out this basis. So I get alpha I beta j minus alpha j beta I times the whole thing, omega I times omega j, like that. If you want to write in terms of tensor component, these are your component of a new tensor. So if you call it like, say, gamma, big gamma, then your gamma ij are this thing, like alpha I beta j minus alpha j beta I. And if you want to write in terms of wedge product as well, you can do that. So all you have to, it's a two form, so all you have to do, write half alpha I beta j minus alpha j beta I times omega I wedge omega j, like that, as we saw earlier. So these are kind of algebra of x, like this wedge product. It will come handy later. It might seem scary at the beginning, but when you get comfortable with it, it's gonna be, it'll come handy. So, okay, any questions so far? We are ready to see some application of these objects. Okay, Arafat, are you following so far? Were you able to follow?
Yes.
Okay, Durjoy? Durjoy, are you here? Okay, Humaira?
Yes.
Were you able to follow? So that's
Yes, I can.
okay, great. Jaber? Jaber? Miss Bajaj?
Yeah. Yes.
Do you have any questions so far?
No.
Okay, Prashanto?
Yeah.
So were you able to follow?
Yeah, I could.
Okay, do you have any question?
No.
Okay, Robin Ray?
Yes, I could follow the calculations. I think it's
Okay, do you have any question?
no, actually.
Okay, great. Sulaiman? Were you able to follow? Okay, do you have any question? Okay. Juthi? Same question. Hello? Okay, I believe we are already losing a lot of students, I think, at this point. Okay, let's see some application, then it will be clear why we are doing this. So we already know.
Can we take a break for a few minutes?
Yes, sure. Take a 10-minute break. Okay.
I have a question about the notation.
Okay, yes.
When we are writing in one form or any p form, we are just denoted by lower bar, any symbol by lower bar. But uh, is is there any way to distinguish the notation between one form, two form, three form? I mean, I get confused. How
Uh,
many form it is?
so no, sorry, actually, basically, if you write a textbook, you have to use boldface for everything except for scalars. Yeah, that's annoying.
Yeah.
No, we are running out of notation here. So
Okay.
usually when I write one form, I'll mention that it's a one form.
Okay.
When I write two
Yeah.
form, we'll say it's a two form.
Okay.
So now we should see some example of two forms. Then it will be more clear why we are doing this.
I have a question.
Yes.
Okay, so we started with gamma is equal to alpha I beta j omega I wedge product omega j, and we finally found gamma is equal to half of alpha I beta j minus alpha j beta I omega I wedge omega j. So basically alpha I beta j is equal to half of alpha I beta j minus alpha j
Yes.
beta I, right? Okay, so this alpha and beta that we use to make this gamma, they are totally independent, right?
Alpha and beta?
Yes.
Yes, yes.
So if that is true, then actually what this suggests is that alpha I beta j is equal to minus alpha j beta I
Yes, alpha I beta j or
is equal to
beta j equals to minus
minus alpha j beta I
alpha j
beta
beta
I.
I. Yes. So why this thing happens? It happens because of the antisymmetry. We have taken an antisymmetric product, not any arbitrary product. That's why.
I mean, say for example, this suggests that alpha 1 beta 2 is equal to minus alpha 2 beta 1, right?
Yes.
But alpha and betas are totally arbitrary. They can be anything.
Yes, they
So,
can be anything, but when you are taking like alpha 1 beta 1, that's gonna vanish. That's why. So just remember, you just do not have just alpha I beta j. You have this part as well. So the product that creates that something else apart from that antisymmetry, that's gonna be killed by this term.
mm, okay, that is true. But say, for example, off diagonal elements, this actually gives very unique solution, actually, unique result. So, for example, if the decomposition of the tensor is unique, then alpha 1 beta 2, that's going to give us a unique component, and alpha 2 beta 1, that's going to give us another unique component.
But
But as
the only thing that is antisymmetric part of that survives. The other part that is killed by that wedge product. Okay,
okay,
let's see an example. Let's see an example. You'll understand what we mean. So let's say our alpha is alpha 1 omega 1 plus alpha 2 omega 2 plus alpha 3 omega 3, right?
okay,
And alpha 1, alpha 2, and alpha 3 could be anything. Then beta, which is beta 1 omega 1 plus sorry, not lower bar, yeah, plus beta 2 omega 2 plus beta 3 omega 3, like that. Now take wedge product. So that gives you alpha 1 beta 1 omega 1 wedge omega 2. See, we our alpha 1 when beta 1 is not necessarily, alpha 1 times beta 1 is not necessarily 0, but that's gonna be get killed by this part. Sorry.
Okay.
Okay. So okay, let's write two more terms that'll clear a few more confusion. So alpha 1 beta 2 omega 1 wedge omega 2 and the corresponding opposite term, so that's alpha 2 beta 1. So I think you want to see this part as well, right?
Yes.
Now if you expand that, then this thing is like alpha uh, alpha 1 beta 2 times omega 1 times omega 2 minus alpha 1 beta 2 times omega 2 times omega 1, right? This is this part, and this part is alpha 2 beta 1 omega 2 times omega 1,
Mm.
then so it should be times minus alpha 2 beta 1 omega 1 times omega 2, right? Like that. We need not to worry about other terms. That will just if you see these four terms, that will be enough to see everything, right?
Okay.
Okay, so if you factor out this thing, you'll see like it's alpha 1 beta 2 minus alpha 2 beta 1. So that's an independent component. Now we have another independent component which might seem independent, but it's really not. That is minus alpha 1 beta 2 plus alpha 2 beta 1 times omega 2 times omega 1. So as you can see, we are left with only parts that are purely antisymmetric. So that's why we wanted to write like this thing. We wanted to write like this instead of just alpha 1 times. So the antisymmetry you are talking about, that where is that antisymmetry in alpha I beta j? There are no antisymmetry in alpha I beta j when you just write like this in this form. It could be anything, but
Okay. Okay.
that antisymmetry is hidden in here because you're summing over I as well. So if you want to show that explicitly that there are antisymmetric, you have to write in this particular form.
Okay. So okay, let's just take a very specific situation. Okay. So let's say alpha has components 1, 2, 3, and alpha has
1 to 3 means this. So omega 1 plus 2
That's right.
omega 2 plus 3 omega 3.
That's right. And beta has components, say for example 4, 5, 6.
That's what I did actually.
No, I'm just trying to see it clearly.
Okay.
4, 5,
For
6. Okay, so what we have seen, alpha 1 beta 2 should be negative of alpha 2 beta 1, right?
no. That's I never said. So the antisymmetry you're talking about, that's hidden in wedge product. You have to evaluate that.
No,
Like you have to
right there, right there. Stop right there. Here, you have written this equation right here. You know,
Oh,
alpha I beta j is equal to minus alpha j beta I.
okay. Yes.
So I can be 1 and j can be 2. So alpha 1 beta 2 is equal to minus alpha 2 beta 1.
Okay, okay. I see the problem. Okay. So the problem is actually why did we get this equation? Tell me. Probably we did this. We equated it with alpha I beta j, right?
That's right. Yes.
Okay. When can we actually equate components? To equate components of two things, we have some like condition, right? What's that?
We should use same basis.
No, the basis system, yes, those basis system are same, and each of the bases are independent of another. That's the point.
All right.
So
Okay.
here omega 1 wedge omega 2 is not independent of omega 2 wedge omega 1. So you cannot do that actually.
Oh, okay. I get it. Thank you.
To equate component, you have to reduce down everything into direct product, because then you know that whenever you see like 1 times 2 or 2 times 1, those are totally independent. But when you have wedge product, those are dependent. So you cannot equate like that.
So this expression is wrong. Alpha I beta j is equal to minus alpha j beta I is actually wrong.
Obviously. So you cannot apply that. It's not true.
All right. Thank you.
Welcome. Okay, try to ask this kind of deep question, then it will clarify many points. Okay, I think our break is over and we can start with our electromagnetism, right? Hello?
Yes.
Okay, so let's not go into Maxwell's equation right now. We'll see Maxwell's equation later, not now. Right now we are worrying about defining electric field and defining magnetic field. So how did we define our electric field and how did we define our magnetic field? What's the definition of electric field? You all know, obviously. Okay. Sulaiman, can you tell me? What's the definition of electric field? Jaber? Jaber? Okay, Prashanto?
Yeah.
What's the definition of electric field? Electrostatic field. Let's not worry about many things together. Yeah.
It's the amount of force on a test, 1 coulomb test charge.
Yes, so force per unit charge, right?
Yeah.
F by Q is defined as our electric field, where F is the force coming from the electrostatic sources only, right? That's the definition. So
Yeah.
what's the definition of magnetic field? What's the definition of magnetic field? How we define our magnetic field? Okay, it's basically the same way. It's again defined like this. Magnetic force per unit charge is basically the velocity of the charge actually small v I want to write, cross magnetic field, right? That's how we define our magnetic field. Okay, so these two things actually constitute the total electromagnetic force. So total electromagnetic force by definition is this, with the definition of electric field and magnetic field, is QE plus Q V cross B, right? So that's in 3 dimension, right? So here our force is basically we are doing everything in vector form right now. We'll convert it into something else. So force is basically dp over dt. Is that a confusion about this?
No.
No. Okay. Then what is the 4-dimensional version of Newton's law? That's the first thing we need to dig up. What's the 4-dimensional version of this Newton's law? We need to remember, at least we know some relativity. What's the 4-dimensional version of this thing? So any idea how do we deal with this? Or should I explain? Okay. Okay, so if I'm not having any answers, so then I assume like I have to explain it explicitly. Okay. So in 3 dimension, there are no Lorentz transformation, right? When we use for slow velocity, we use Galilean transformation. But when velocity is high, we have to treat everything in like we have to consider that Lorentz transformation, right? So do I need to explain Lorentz transformation and Galilean transformation as well? You can ask actually. It's okay. It's pretty okay to ask for it. It's not a problem for me. I just wanted to skip, but if you need it, then I can explain it.
I'm fine. Like, no need to explain both of those things.
Okay. So you want to see the explain or you're not? You're fine means?
No need to explain Galilean and Lorentz transformation.
Okay, okay.
Yeah.
At least I
For
can
me, yeah.
transformation directly, right? So
What did you say?
So if I write the proper time in 4 dimension, and that's invariant, everyone is comfortable with that, right? So in flat space time, when we talk about spatial relativity, there is a thing that doesn't change under the change of observer's velocity. So if a particle is moving like that, every event or every point in a 4-dimensional space can be recognized as time of the seen by the observer, position of the particle, like this. This is an event, right? So in our view, this t, x, y, z is nothing but a bunch of coordinates. That's just 4 dimension. You treat time as like any other coordinate. But Lorentz transformation, that's actually something physical that tells us that whatever observer you use, this distance, that is this proper time, like d tau square, defined as dt square minus dx. Actually, I should write in opposite way. So how should I write? Okay, let's write this way. Okay, dt square minus dx square minus dy square minus dz square. This is the object that everyone sees same. This is the distance everyone sees same for a single particle. So if a particle is moving and someone is remaining static at this point and someone else is moving, both will see this d tau square to be same. Like this thing under Lorentz transformation, this thing is true. We call it the proper time. Okay, let's make it intuitive. So proper time is the time of that particle in the frame of that particle itself. So consider like you are watching a planet moving, and on that planet there is a clock. You are watching on that clock. So when that clock, like it was at 12 o'clock, then it becomes 1 o'clock. So the interval is 1 hour. You see that that clock shows that interval is 1 hour. So whoever seeing that clock will see the same, that it was at the beginning it was 12 at 12 o'clock, then it became 1 o'clock, right?
Yeah.
Their own time would be something else, but the reading, if they take it from that planet's clock, that would be same for everyone. So if the object that you are observing, if you use their time, that's actually a universal parameter.
Yeah.
And that's a good thing to use universally as well. So that's why we use in 4 dimension to define everything, we use proper time instead of ordinary time. So proper time, d tau is the proper time. So basically we are parameterizing any particle's trajectory with the time seen on its clock. That's all. And that interval in that clock is known as d tau, infinitesimal time separation seen in the moving frames clock. Okay, so now we can define velocity the same way we defined here. So these are the coordinates. So our coordinates are t, x, y, z. So what we can do is velocity, which is point or event, differentiated with respect to tau, the proper time, which is the parameter along the trajectory of that particle. That's we define as our velocity vector. And if we expand the same way we did earlier, then it will become like delta p tilde by delta t dt by d tau plus delta p tilde by delta x dx by d tau plus delta p tilde by delta y by dy by d tau plus delta p tilde by delta z dz by d tau. Is that clear to everyone? Here tau is the proper time parameter, or the time of the frame of the object we are actually observing. So whoever observing that thing will see the same, because we're watching at the same clock. So we should agree. Okay, so we can define this thing to be a basis, right? Basis along the time axis, right? So we call it ET. And then this derivative with respect to tau, we can call it like dot. So let's call it T dot. Then we have like Ex, which is the basis vector along x-axis, then x dot plus Ey, y dot plus Ez, z dot, right? Now, so these are the basis vectors, right? These are the basis vectors. Et, Ex, Ey, Ez, right? So question is, how do we take a dot product of a vector? So, and in another way, what's the metric tensor? What's the metric tensor here? What's this thing? So we know already that d tau square is the thing that everyone sees same, right?
Yeah.
So we can use this information. So d tau whole square, if we divide the whole thing by d tau square again, so d tau over d tau whole square, which is what?
One.
Which is 1. Okay, and then we have dt over d tau whole square minus dx over d tau whole square minus dy over d tau whole square minus dz over d tau whole square. Is that correct?
I think so.
Okay, that means we can from this expression we can conclude that negative t dot square plus x dot square plus y dot square plus z dot square equals to what?
-1.
Yes, -1. And these are the velocity components, aren't they?
Yeah.
Okay. So this is the object that should remain under any transformation, right? So basically what we want to have is a dot product between the vectors. So we want like this. So what would be our metric tensor then?
Well, it will be diagonal, and the first diagonal component will be -1, and the last three will be plus.
So tell me this thing, ds square. Tell me this thing.
In the components.
Yes.
Okay.
It will be
G.
minus dt times dt plus dx times dx plus dy times dy plus dz times dz. This is our metric tensor.
Yeah.
Is that clear to everyone?
Yeah.
Okay. So this metric tensor is basically saying that that proper time is invariant. That thing, proper distance is invariant. Whatever you say. So that comes from the Lorentz transformation basically. Okay. So we have our ds squared then. So that is I don't want to write again. Okay, let's write it. Okay, so we can actually then find the corresponding momentum as well, right? If a particle has a mass m, then you can find the momentum as well. Is that clear to everyone? So what's the definition of momentum? What's the definition of momentum? When momentum one form, what's the definition? You remember we already shown that from Lagrangian mechanics, this thing is true. So it's basically mass multiplied by velocity, but before, as we want our momentum to be one form, we convert our velocity to the one form thing.
Yeah.
Okay, so what it should be then? You know your velocity, you know your mass, then what it should be? Like the momentum. Do I need to show it explicitly? So you have your mass, then dt times dt. In the second slot, you are actually supplying V. So you are piercing V with this part only. Then dx times dx, but you are now in the second slot, you are supplying V. So pierce with that, and so on. So plus dy times dy pierced with V plus dz times dz pierced with V, like that. Is that clear?
Yeah.
Okay, what's the result then? What's the result then?
Those piercing will be components. T dot, X dot, Y dot, Z dot.
Yes, so it will be like n times, when you pierce it, dt to V, it will be just component, like time component of V, that's T dot, right? So it will be like negative T dot dt plus, when you pierce that, you get X dot dx
Dx,
plus Y dot
dy.
dy plus Z dot dz, right? Like that. That's our momentum. So we extend our Newton's law in the same manner. We just take derivative of dp with respect to d tau. That's we define our force in 4 dimension. So force is defined to be, we'll write it as curly force, which is a one form, and the relation is this thing. Take derivative of momentum with respect to proper time. So now if we have some electromagnetic source for this force, we can actually expand those in terms of our velocity components. So first we need to understand what those components are actually. So let's expand it. So because we are going to use it here, so we need it actually. So for a slow moving object, So the object you are observing, that's moving really slow. Then what's your t dot? Hmm?
1.
It's 1. And what about the other parts? What is your x dot? X. So okay, let's try to understand it in a better way. So it's basically dx over d tau, but from the above expression, this thing is nothing but this thing, dt over d tau. So when the object you are observing, it's moving slowly, then the watch on your hand and the watch sitting on that object, they ticks at the same rate, right?
Yeah.
Almost the same rate, approximately. So those times are same. So then we can actually approximate it as, like as we did here. This is approximation, right? So dx over d tau can be approximated as dx over dt. That's our usual velocity. Like when I measure a velocity of an object in 3 dimension, I just take my watch's reading and my observation of change its position, and I take ratio, right?
Yeah.
Okay, so it's basically Vx, 3 vector form, in 3 vector form. So first we need a conversion between 3 vector and 4 vector that will give us a better understanding of this, how to generalize this Lorentz force law. So from now on, if I write v vector like this, it means we are actually talking about 3 vector. Means we are having like this vx ex plus vy ey, like that. And if I write like this, it means I'm talking about 4 vector, and that has like a time component as well. So it's then actually I'm a little bit careful about my indices, so I do not write slopily like that. So I write like this, vt, et, and so on. So now, if the object were moving slowly, then 4 velocity has components like 1, then vx, which is a part of 3 vector, vy and vz, like that. 4 vector can be written like that,
Yeah.
approximately. When vx, vy, vz are tends to 0. Okay. Now, we have our Coulomb-Lorentz force law like this. dp, when I write like upper bar, it's actually, let's write like this. So it's in 3 dimension I'm talking about. In 3 dimension, we are having like this thing. Electric field is defined in 3 dimension as well. This v vector is the 3 velocity cross b, like that. So as you can see, this whole thing is proportional to 4 velocity, right? Can you see it? It's linear in the component of Vx. there are no Vx square or Vy square.
Yeah.
Also, we have a term that's just E. So we can write that term as also like linear in V as the leading component, the zeroth component, that's approximately 1. That's why. So we could write like this. Q, let's factor out that part. Then we have like 1 times E plus V cross B, like that.
Yeah, we could.
Okay. So what we are expecting, a 4-dimensional version of it, is this. So rate of change of momentum 1 form with respect to tau, which is the 4 force, which should be equal to, number 1, they should be linear in Q, as we have here, then linear in velocity, and linear in the field component. But field component are multiplied by the velocity components. So we are assuming field F. Here are 2 kind of F. One is curly F and there is ordinary F. Curly F is the force and ordinary F is electromagnetic field. So electromagnetic field, and see, the result is a 1 form and it's taking a vector. So what object should it be? It's taking a vector for velocity and producing a 1 form. So what object should it be?
One form.
No, if a 1 form takes a vector, then that becomes a number only. But we are not having just a number. We are still having a 1 form. That's it. So what this object? What is this object? This one is a 1 form. Or this is 1 form. This is a vector. So what kind of object that should it be? That ordinary F, like field F, should be?
Two
Two
form.
form.
It's not necessarily 2 form.
That
It's
means
generally a 0-2 tensor.
tensor, yeah.
That's what you should say. It's a 0-2 tensor, right?
Yeah.
Okay, so now we are almost ready to define what our F is. So we at least know its characteristic. It's a 0-2 tensor, and that's a lot to know actually. Okay, so as it's a 0-2 tensor, we can write F, the full object, like this: F mu nu dx mu times dx nu, right? Where x mu are the coordinates that t, x, y, and z. So basically, what I mean is, okay, let's write it more explicitly. Actually, then you will understand what I mean. Is if I write x0, that's my t. If I write x1, that's my x. If I write x2, that's my y. And if I write x3, that's my c. That's what I mean actually. It's just a shorthand notation, nothing else. I could write explicitly, but that's just a shorthand notation.
Yeah.
So from this assumption that F is a 2 form, we can try to write this thing explicitly and try to compare with our original Coulomb-Lorentz force law in 3-dimensional. So the 3-dimensional part should match. That's our trial. So okay, if I have my velocity vector to be like this, v mu e mu like that, then I'm actually, what I'm doing is I have q, I have f, it has 2 slots, right? I'm keeping one slot empty, putting v on the other slot and trying to evaluate what happens. Right? Is it clear to everyone at this stage? Or we are lost totally?
I guess I missed one line. Can you repeat it?
Which one?
The previous. I mean, what have you said now?
So I'm saying like our guess is like f is a 0-2 tensor, and as arbitrary 0-2 tensor can be written as dx mu times dx mu with its components.
Yeah.
And I know my vector really well, so my vector can be written in terms of components like this.
Yeah.
Where v mu, these components are basically x mu taken derivative with respect to tau. That's what it means. Because we had those dots. So now I can expand, right? I can expand. So when I'm taking this piercing, it basically means this: f mu nu dx mu times dx nu, but pierce with vector v, right? In abstract form.
Yeah.
And that's actually q f mu nu dx mu. And what do I get from here?
Component v nu.
V nu, like that. So now this object is obviously, as we try to construct, it's linear in velocity components, component of the velocity, it's linear in charge, and it's linear in field. We are trying to identify f mu nu, that's our goal. Okay, so on the other hand, we have our dp over d tau, right?
Yeah.
So on the other hand, let's write it dp over d tau, rate of change of momentum with respect to proper time. Okay, so we can actually expand our momentum part as well. So okay, let's remember what those p tau, like components of p. What's this p? So what are the components? So usually we write like this. So p nu dx nu, right? But what are those p nu?
Yeah.
Like p nu, what's that? Can we find it from the above? Because we had our, yes, we have written our p over here. So can you identify what's our pt? What's our px?
Yeah, minus mt dot.
Minus mt dot. Okay, great. Then px?
Mx dot.
Mx dot. Okay, then
My dot. Mz dot.
my dot, then mz dot. Great. So these are the components of momenta, right? Remember, zeroth component is a negative one. So that's the important thing we have to remember here. So negative t dot, right? P0 is negative t dot.
Yeah.
So let's write like this. So dd tau of
Is it
negative.
minus mt dot?
Okay, yes, mt dot. So I can I can pull out m outside of the derivative, right? I just factored out that part. Okay, minus t. Sorry, t dot et. That's what I wanted to write. Or actually, let's write this one. Minus m t dot. Where did that minus sign go? Okay, let's write it again. Minus mt dot et. Is not et, like it is dt, right? Plus mx dot dx plus my dot dy plus mz dot dz, right? Okay, great. I can take the derivative inside of this thing. So instead of single dot, we'll have double dot, because mass is not going to change, obviously. We are considering like 4-dimensional version. So the definition of mass is it's a parameter that doesn't change. Okay, and the bases are like Cartesian bases, so they are not going to change as well. So the only derivative we can take is on the coordinates, right? So if you take the derivative, it will be like on the left hand side, it will be like minus m t double dot dt, right? Then plus m x double dot dx plus my double dot dy plus mz double dot dz. Is that clear to everyone? I just took the derivative.
Yeah.
Okay, now this side I want to write it explicitly. So we have our sum over mu. So q times, if I expand the sum over mu, what will it be? It will be like f0 mu, or no, let's take the let's expand this part first, like mu first. Okay, that's any part we can do. Actually, we have to do both actually. So actually, it becomes like f mu 0 dx mu, and then v0 plus f0 sorry, f mu 1 dx mu mu 1 plus f mu 2 dx mu times v2, right? Plus f mu 3 dx mu no, we have to do both, but I think this way it'll gonna be messy. I'm really sorry actually. So I wanted to equate like dxy dxc. So sorry, please cross this part. Actually, I want to do it other way. I wanted to show it explicitly. So yeah, so I want to write I'm expanding the sum over mu, not v. So it becomes f0 mu dx0 v1 sorry v nu, I can write like that, plus f1 nu dx1 v1 plus f2 uh, uh, f2 nu dx2 v2 plus f3 nu dx3 v1 plus f4 nu dx4 v1 plus f5 nu dx5 v1 plus f6 nu dx6 v1 plus f7 nu dx7 v1 plus f8 nu dx8 v1 plus f9 nu dx9 v1 plus f10 nu dx10 v1 plus f11 nu dx11 v1 plus f12 nu dx12 v1 plus f13 nu dx13 v1 plus f14 nu dx14 v1 plus f15 nu dx15 v1 plus f16 nu dx16 v1 plus f17 nu dx17 v1 plus f18 nu dx18 v1 plus f19 nu dx19 v1 plus f20 nu dx20 v1 plus f21 nu dx21 v1 plus f22 nu dx22 v1 plus f23 nu dx23 v1 plus f24 nu dx24 v1 plus f25 nu dx25 v1 plus f26 nu dx26 v1 plus f27 nu dx27 v1 plus f28 nu dx28 v1 plus f29 nu dx29 v1 plus f30 nu dx31 v1 plus f32 nu dx32 v1 plus f33 nu dx33 v1 plus f34 nu F2 new dx2 v new plus F3 new dx3 v new, right? I can write like that. This thing is a whole one form. So now let's simplify things. So if I simplify, the first term is like fq f0 new v new. This is the component and the basis is dx0 plus q f1 new v new times dx1, like that. Then if q times f2 new v new times dx1 plus did I make a mistake?
Should be dx2.
And what's the last?
Yeah, dx2, I think.
Yes, it should be dx2. And what's the last term?
Q f3 new v new
V new
dx3.
dx3. Great. So now on the both side we have one forms, right? With the same basis, so we can equate, because one form basis, those are like dt, dx, dy, those are independent basis, right? In 4 dimension.
Yeah.
And dt is just dx0. So let's write the same way. So on this side we can write like this: minus mt double dot dx0 plus mx double dot dx1 plus my double dot dx2. So basically y is x, right? Y is x2 and x is x1 and t is x0, like that. So now we are in the place to equate on both sides, right? Like compare component wise. What's the equation in 0th component? What's the equation in 0th component?
Minus mt double dot
Minus mt double dot
minus mt double dot.
Oh, minus, yes, obviously. My mistake. Minus mt double dot
is equal to
equal
to f0 new
f0 new
v new.
v new. Now it's time we expand this thing as well. So q f00 v0 plus q, or let's factor out q, then I do not have to write it again. So f01 v1 plus f02 v2 plus f03 v3. I can do that.
Yeah.
We can do the same thing for the rest as well. So minus, sorry, in this part would be plus, right? Plus mx double dot equals to
q v1 new
v1 new
v new
which is
f10 v0.
No, the new is the second index, so it's 0 1 0 1 0. Oh, sorry, yes,
10
1 0 v0, yes, exactly.
Yeah.
Then f
1 1
1
v1
v1 plus
f1
1 2 v2 plus
1 3 v3. Yeah.
And then my double dot just hang on, it will pay off. It might be messy for a moment, but it will pay off. Okay, so this thing, then F22 V2 plus F23 V3, right?
Yeah.
Then
MZ double dot.
MZ double dot Q 3 new
P new.
Q F3 new V new, which is
30
30 V0 plus
31 V1
F31 V1 plus
32
F32 V2 plus
F33 V3.
F33 V3. So this was absolutely in relativistic version. So what I want to make is an approximation that it's now moving in a slow velocity. It's not that fast. So